Hey everybody, we're going to talk about stoichiometry and enthalpy in video note 6.2. So here's the objectives. Here's what you should be looking at, chapter 9, sections 1, 2, and 3, and try this exercise, self-check exercise. And there's an example to refer to. Okay. Oh, look at these two cute dogs. They're going to tell you that in the real world, chemistry is awesome. That's a connection. So why do reactions happen? Reactions happen because of energy. So the relationship between stability and energy is that low energy is more stable equals more stability. So one of the driving forces of reactions is because things are going towards more stability, which is low energy. So energy is conserved in a chemical reaction, much like masses. So you might be saying to yourself, why are some reactions explosive? Well, some reactions are explosive because the result of that reaction is much more stability for the chemicals that are formed. And it releases a lot of energy in it quickly. All right, so bond energies. Here are a bunch of chemicals bonded together. We got single bonds, double bonds, triple bonds, and bond energy is the energy it takes to break that bond. So that means it takes 391 kilojoules per mole of energy to break a bond between N and H. Okay. So you can see what when the bond is formed, this is the most stable position, and that's the low energy, is when the bond is formed. And so in order to break that bond, you have to add energy in. So we can do an energy diagram. And an energy diagram shows overall what's happening to energy in the reaction. So you have reactants turning into products. And here's their energy on this side. So reactants turning into products. You can see in this reaction that the products are more stable because they have lower energy. And so this part right here is the energy that's released when the products are forming. This is called an exothermic reaction because overall energy is released and the products are more stable than the reactants. This is called an endothermic reaction because if you notice, the products are less stable than the reactants. They have more energy stored in them, and so they had to absorb energy from somewhere in order to be created. Okay, so this is endothermic, and energy is absorbed, and so the products are less stable than the reactants. Okay, so calculating bond energies is something we can do to find out if a reaction is exo or endothermic, or whether energy is absorbed or released. But we have to know what the molecules look like. So an H2 molecule looks like this, and it says there's two of them. Okay, two of those. An O2 molecule looks like this. So our dot structures are going to help us in this situation. A water molecule, H2O, looks like this, and in this reaction, two of them form. Okay, so these numbers tell you how many molecules, and the formula tells you what the compound looks like, or the molecule looks like, and then the bonds. So if I want to calculate the bond energy for this reaction, I have to break these two bonds. So it's going to take 2 times the 436 kilojoules to break those bonds open. And I have to break this double bond, and that's going to take 499 kilojoules of energy. And so then I have 872 kilojoules of energy that have to be absorbed to break those, plus the 499. Means in order to break all these bonds, it's going to be 1,371 kilojoules of energy. Okay. Now, I don't have to break any water bonds, but when water forms, these bonds form and that releases energy. So anytime we're releasing, it's losing, that energy is negative. So if I look at OH, it says 463, but if I want to break them, so if I want to make them, then it's negative 463. So I got 4 OH bonds times 463 kilojoules of energy released every time one of those bonds forms, and that's 1852. But what happens is that's negative because it's being released when the bonds form. So overall, in this reaction, it's going to absorb 1371 kilojoules of energy to break the bonds, and then 1852 kilojoules of energy is going to be released when the new bonds form, So this overall reaction releases more energy than it takes in. So we call this exothermic because more energy is released than gets absorbed. So this is an exothermic reaction. So what would an energy diagram look like for this? Well, we have energy on this side, energy, right? And then we have reaction progress. Okay, so our reactants are going to be higher than our products, and every reaction goes uphill first and then down. And so then this difference right here is that 481 kilojoules of energy that's released when the overall reaction happens. How does that look in the reaction? Well, if the energy is released, it's produced. So there's 481 kilojoules of energy. And then this would be negative 481, showing that it's released. Okay, let's try. You guys try this one. I'm going to draw out this molecule for you. So we have 3 carbons. The first carbon has 3 H's. The second carbon has 2 H's, and the third carbon has 3 H's. And oxygens, but there's 5 of them. So what? We have to draw it 5 times, right? All right, those are the reactants. You got to break all those bonds, and that'll turn into products. And for products, we have carbon dioxide, 3 of them, right? And 4 waters. So we did water on the last one. But what I'd like you to try, I know it's going to take you a little bit, but you can do it. Pause the video, get your calculator out, and add up to see how much energy it takes to break all of these. Add to break, because you got to break all of these bonds. And then it's going to make these bonds, so this is going to be released. Release the energy here. So there's a 1, 2, 3, 4, 5, 6 CO bonds that form. So it would have to do that times 6. But it's being released, right? So it's negative. And then get the total. You have to take the breaking and releasing together to get overall. Okay? So try it, and then I'm going to tell you what I got. I got negative 2054 kilojoules per mole. And so I want to see if you can get that. If you get something different, let me know, and we'll talk about it. Okay. So then I also want you to sketch the energy diagram for that reaction. Right? So if it comes out negative overall, right, then it's going to be exothermic. So that means products are going to be lower. After you calculate if it comes out positive overall, it's going to be endothermic. So products are going to be higher. Try it and see. So now that we know about heat and we know about chemical reactions, we can talk about stoichiometry. Stoichiometry is the math of chemical equations. So if you're starting with 50 grams of salt and 3 crackers, how many Cheez-Its are you going to make? That's what that mouse wants to know. But really, stoichiometry is taking a balanced chemical equation, woohoo, look at that, and some amounts of chemicals, seeing how much of this can come out, or how much of this do I need to make a certain amount of that. You're going to need to know what you're trying to find, and you're going to need a periodic table. Okay, so let's get going. I'm going to do an analogy for tricycles because all bears need tricycles. So if we have this equation for making tricycles, wheels plus a frame, 3 wheels and a frame give you a tricycle. If we have as many frames as we need, infinite number, how many tricycles can Mia make when she has 9 wheels? All right, so we're going to say, well, I have 9 wheels. I want to make tricycles. So I know from the balanced equation that there's going to be 3 wheels for every 1 tricycle. Where did I get these numbers? Well, they're the coefficients in the balanced equation. So I find out I'm going to be able to make 3 tricycles with 9 wheels. That's stoichiometry. All right, woohoo, yay! Now, I can only make 3 tricycles if I have enough frames, but it says we have enough frames. Right, so this is the tricycle equation, and I'm showing you that these coefficients, these ratios, help us change one thing. We turn wheels into tricycles by using those coefficients. Okay, so in chemistry, it's not a wheel-tricycle ratio, it's a mole ratio or a heat ratio. We can convert one chemical into another, or a chemical into heat, or heat into a chemical using conversion factors of mole ratios. And they have to come from a balanced equation, and the numbers are the coefficients. So, oh look, it's a balanced equation with some heat in it. We can make a mole ratio. So you find one substance. We'll do iron to oxide. So there's 3 moles Coefficients are moles, 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 and heat is a coefficient as well. So for every 3 moles of FeO, I'm going to be able to make 3 moles of Fe. So I could take any two things in the equation and make a ratio out of them, but it has to be moles or heat. So let's take aluminum oxide. So 1 mole of aluminum oxide can be compared to anything else. Let's compare it to iron. No, let's compare it to aluminum. 2 moles of aluminum. But wait, can't I say 2 moles of aluminum for every 1 mole of aluminum oxide? I sure can, right? Can I say 3 moles of iron 2 oxide for every 55 kilojoules of heat? I sure can. Or I could flip all of these. So mole ratios and heat ratios are the coefficients or the heat in a balanced equation used as a conversion factor. And so here we go. We have a balanced equation with some heat. This heat says positive 195.3. Okay, so we just talked about heat. We said when it was negative, it was exothermic, so the heat was produced. When the heat is positive, it's endothermic, so the heat really is one of the reactants. It has to go into the reaction in order for the reaction to happen. So now we have a complete balanced equation with heat and coefficients. This says if 12 grams, so given 12.3 grams of potassium chlorate, how many grams, so find grams of oxygen will be formed. Okay, well we have to change the chemical oxygen into the chemical potassium chlorate into the chemical oxygen. Start with your given, 12.3 grams of KClO3. I need to change it. But these coefficients mean moles and they mean kilojoules. This is grams. So this is where our mole practice comes in, because I can't change one chemical into another unless I'm in moles, because coefficients are moles. Right? And so I'm going to have to change grams into moles. And then I want to get rid of the moles I was given, see you later, change them into moles that I'm trying to find. And last but not least, if I want grams, I gotta change moles of oxygen into grams of oxygen. So see what's going on here? We're taking one chemical, changing it to moles, and then we're using the relationship between moles in a balanced equation to change one chemical into another, and then the periodic table so that we have grams. Where do the numbers come from? Well, we know every time we go get grams from the periodic table, it's for 1 mole. And then I add up K plus Cl plus 3 O's, and I get 122.55. Okay, so this is 39.10, 35.45, 16 times 3, boom. Okay, so now I have moles of KClO3. Well, coefficients are moles. So now I could change KClO3 into oxygen because there's 2 moles of KClO3, but it has to be KClO3. Woohoo, where'd that come from? Right there. So what do I put in front of moles of oxygen? A 3. 3. Okay. Now I've changed my identity. Okay. Changes chemical identity. Chemical identity. All right. Now I'm moles and grams. Anytime it's moles and grams of the same chemical, number 1 goes with moles, and I got to go get grams from the periodic table. 16 times 2. 32. All right. Then I do the math. Cancel out the units. Yay, grams of oxygen. 12.3 divided by 22.55 times 3 divided by 2 times 32 gives me 4.82 grams of oxygen. So what that's saying is if I put in 12.3 grams of that, I should get out 4.82 grams of oxygen. Woohoo. All right, that's stoichiometry. See if we can do some more. I want to make 4.353 grams of potassium chloride. Okay, so this is given. What do I know? How many grams of, so find grams of KCl3. All right, so 4.53 grams. Ooh, I feel like this is coming right out. 4.35 grams of KCl. That's given. I want to change that into moles because the only place where I could change a chemical identity is if it's in moles. And then moles of KCl can change into moles of KClO3. So this is coefficients needed. Coefficients needed. Right. And then, once I have moles of KClO3, I can cancel those out and change them to grams. Right. So, let's get busy putting in some number. Anytime it's moles and grams, we have to find out for 1 mole how many grams. Go get it from the periodic table. And it's 74.55. Then moles to moles, we got to use the coefficient. So here's a 2 in front of KClO3. So 2 in front of KClO3. 2 in front of KCl. And then grams and moles, I go get it from the periodic table. And I find out it's 122.55. And then goodbye grams of KCl. Goodbye moles of KCl. Goodbye moles of KClO3. And hello grams of KCl. Okay. So then we do the math. And we get 7.45. Hey, can we do stuff with heat? You betcha we can do stuff with heat. So it says how much heat. Find heat kilojoules. Okay. Given grams of KClO3. All right, so again, start with the given 58.6 grams of KClO3, potassium chlorate. In a balanced equation, you don't have grams, you have moles. So we have to change it to moles. Now that we have moles, we can get rid of moles of our given and change it into kilojoules. Okay, so let's get some numbers. Anytime it's moles and grams, moles are number 1, and I got to go get the grams on the periodic table. Oh, look, it's kilojoules and moles. What? Balanced equation. Moles of KClO3 is 2. So I put a 2 there. Kilojoules is 195.3. Okay. So these come from coefficients, the heat coefficient and the coefficient. And then goodbye grams, goodbye moles, hello kilojoules. And it is 46.69 kilojoules of heat needed to go in. Okay. All right. So here's another one, but it's this time it's asking given heat, given kilojoules, find grams of oxygen. Okay. So I'm going to set it up, and you guys knock it out. All right. So you're given the kilojoules. Anytime you have kilojoules, you can cancel out kilojoules because it's part of the equation. It's over here, 195.5 kilojoules. And then that's per mole of, this time we're going to oxygen. Right? And then mole of oxygen can turn into grams of oxygen. And so then over here, I put mole of oxygen is a 3, and then kilojoules 195.3. Oh, I put 5. Okay. Grams and moles. Moles is number 1. PT 32. All right. So go ahead and see what you can get from that. All right. When I did the math, kilojoules cancel, moles cancel, and I get 14.18 grams of oxygen. Okay, that's stoichiometry. Use your balance equation. Use your mole stuff. All right. We have one more thing to do to make sure we can do these problems is molarity. Okay, so given 250 milliliters of 1.5 molar silver nitrate, and then we have excess barium chloride. So how many grams of barium nitrate will form? So find. All right, so we want to change the identity. We want to change silver nitrate into barium nitrate. So we need to change the chemical identity. So we start with the 250 milliliters. It's a little different because we have molarity now. We know there's 1,000 milliliters in 1 liter. And now we know that there's 1.5 moles of silver nitrate for every 1 liter of solution. Okay, so now we're in moles. So you know, right from moles to moles. Moles of silver nitrate can turn into moles of barium nitrate, so long as we use a balanced equation. And then moles of barium nitrate can turn into grams of barium nitrate. All right, numbers. We need some numbers. Over here, moles of one kind and moles of another. So I look for silver nitrate at 2. Barium nitrate, 1. Grams and moles, let's go get the grams from the periodic table. And when I do that, I get 261.32 grams. Okay, milliliters cancel milliliters, milliliters cancel liters, moles cancel moles, moles of barium nitrate cancel. And I'm left with 48.998 grams of barium nitrate. Okay, that was a little tougher because we had the molarity. You have to know molarity and what it means to do that one. Okay, here are 2 example problems. I want you to try these, and I'm going to give you the, we'll look at it when you, we'll do these ones in class to see if we can do them. All right, so make sure you know that coefficient ratios are needed to change the identity of a substance. You can change something from one chemical to another or something to heat. Coefficients work from moles to moles, heat to moles, and moles to heat. If you're given grams, you have to change to moles to use them. So that's important stuff. All right, so review. Go through moles, know your coefficients, use your periodic table, use concentration as a conversion factor, boom. Okay, this map might help you. So usually we're given grams of one substance and we want grams of another. So we have to change to moles, moles of one to moles of another, and then grams of that stuff. All right, so really know that chapter 9 is fine. Know these objectives, and peace out. That's the target. We're trying to learn it, get the learning.